We'll begin example 3 here by doing the same thing we've done in all of the last videos. We're going to try to draw a picture of the region that's being communicated here and what the 3D solid would look like. So I'm going to find the volume of the solid that's obtained by rotating the region that's given here, which lies to the right side of x equals 1, about the line x equals 1. All right, so let's see what we have. We know here that we're dealing with the parabola y equals x squared. So let's assume that it looks something like this. And I'm going to have the line y equals 9. For the sake of argument, let's just say that that's up here. And it looks like I can already start to see a region that's bounded by these two curves. However, I want it to be to the right side of x is equal to 1. So if I kind of imagine x equals 1 as an additional line that's going through here, I can see that my space is actually going to be just this little space right in here. In fact, most of the rest of this picture I could completely erase as I don't seem to need it. But now I can go ahead and I can start to generate a 3D picture of what would happen if I was to take that region and revolve it, notice here, about the vertical line of x is equal to 1. So I'm going to rotate it in this direction. Okay, so to try to do this, again, I'm going to try to draw a dashed line right around where I would imagine x equals 1. Okay, so there's my dashed line. That's what I'm going to rotate around. And I'm going to kind of create here a copy of my parabola piece that was located there. And then I'm going to think about what would happen if, again, I'm attempting to spin it around that axis. So, no surprise, I'm going to need a duplicate image on the other side, something maybe kind of like this. And then I can start to play connect the dots. I find a point in its mirror image, and I have one thing that pulls out of the page, and then a dashed line to go back into the page. And I'm going to do this again for a couple points on here and their mirror images. I'm going to play connect the dots, and then go back. So I'm just going to do this 2 times on here for the sake of space. So what I can start to see then is something is very interesting here. I still see that I have this kind of a shape of a circle in play. But notice now that my circles are stacking differently than they did before. Notice here, in the previous question, my circles kind of stacked to the left and to the right of one another, right? That is, they stretched down the x-axis. However, here, my circles are stacking vertically on one another, right? That is, I have like a circle and then another circle on top of that, and on top and on top and on top, right? I got a bunch of circles stacking in the vertical direction. And so because of that, this is very likely then going to be a dy question. That is, a question that I have to set up an integral for with respect to y. So I'll state this. Since our circular cross-sections stack vertically, we will set up an integral with respect to y. So let's try to see what this particular solid actually looks like using the online applet. So let's go ahead and switch over to that and see kind of how it would be similar and different to what we did back in example 1. So if we switch over here, we again can start to see that we have our region in the xy plane drawn out here, and that we can go ahead and insert our region by just clicking this little check mark, and now we can see it in there. However, what we're going to notice is that we're going to be, again, dealing with kind of circular cross-sections that stacked vertically, and we said this would be a dy problem as a result. We tackle this integral with respect to y. So one of the main features of a problem that is done with respect to y is that we'd have to actually come down here to this very bottom option. You see, right now we have our functions in the form of y equals a bunch of stuff with x. When we do a problem with respect to y, we're going to be switching that to have functions that are x equals a bunch of stuff with y's in them. What this is going to require is that we take our different functions that were located within our initial region and attempt to solve them for x. So we'll see here that we're going to have what we refer to as a right region and a right side and a left side of our given region. Now let me go ahead and kind of show you what this would look like. For our purposes, we're going to go ahead and take that equation that used to be y equals x squared. And if we solve that for x, we're going to get x equals the square root of y, technically plus or minus, but as you can see from the original picture, we would know, that we're only dealing with this positive portion that's existing over here. So I have x equals square root y. The other formula that I have that kind of forms the left side of my region is that vertical line at x equals 1. So we can go ahead and take a look at what the picture looks like here, but we'll have to make a couple quick adjustments to this. We note that our value of y is actually going to be going from the number 1 all the way up to the number 9. Now notice that once I did that, the region that I had here changed drastically. And again, if I go over here and start scrolling out, I can see the full region. Wow, there it is. So again, since it's not fitting well within the box, I'm going to go ahead and adjust the window here. It looks like I'm only going to need x values maybe from like 0 over to 3. I'm only going to need y values from maybe 0 up to 9. And if I do this, again, I can kind of scroll out here a little bit and I can see my region much, much better. There's the region that we have. Now, over here, let's get that out of the way. Over here on this side, what I can go ahead and do is change my axis of revolution, what I'm rotating around. Remember, I'm rotating around the line x equals 1. And so when I do that, notice that I include this kind of dashed line, just like we did in our picture, to kind of what we're rotating around. Now, much like what we saw in example 1, we can show kind of the different representative rectangles here that we could draw. And notice that those rectangles are shown in red over on the side. These rectangles here are just at different heights, but based on what height they're at, they're longer or shorter. And when we revolve that rectangle around the axis, we are still creating a circle, but notice now it's a circle that's going to exist, well, stacked on top or below other circles, right? We can imagine that we're going to have very, very small circles at the bottom and circles with much larger radii up at the top. So if I was to go ahead and imagine doing this at every single point, if I rotate the entire region around, here is the solid that I end up with. Right? I can see it here. This is the solid. And so we're going to be interested in now trying to ultimately figure out how exactly can we try to find the volume of that solid. And of course, it will come back to understanding what's going to happen when we revolve around one of those little rectangles. Can I find the area of one of those circles, multiply it by a little width to get that volume for that individual slice? Let's take a look at that. Okay, let's go ahead here and try to then think about what exactly I would need if I wanted to go ahead and set up a volume that was going to ultimately be dy. Okay, now again, I know that one of the things that I'm going to need on the inside of the integral here is a formula for the area of that cross section. Well, that's still going to be the area of a circle, so I'm still going to have pi r squared, but I need to think about how I get that r. I'm going to go ahead and draw in the radii for all the different circles that I can see here. And I'm going to draw them so they go back from the axis to the original function. And this is important for us to be able to do here. I always want to go back to the original function. So I'm going to sketch out some radii then that look like this. And notice I want to find how long those radii are. Now they're not all the same, right? Radii maybe near the top are going to be a little bit bigger than radii that are going to exist down near the bottom. So in order to figure this out, I'll notice that I'm going to need an x coordinate for these red points on the left side and x coordinates for red points that are on this outside, this right side. Now, on the left, that's pretty easy because all of my radii are going to be right there on the axis of rotation, and that means that they're all going to have x coordinate 1. But all the other x coordinates kind of vary, and they're kind of modeled by this function. But notice that this function right now is set up to say, you give me an x coordinate and I'll tell you a y. And what we would like to do instead is to solve our y equals x squared for x. Now if we do this, that of course is going to give us x is equal to plus or minus the square root of y. However, if I was to go ahead and notice that I'm only dealing with the side with positive x's, then I know that we just need x is equal to square root y. So notice then that if I knew the y coordinate where I was looking at a particular circle, if I could plug in that y into this formula, it would spit out the x coordinate associated with that right side of the radius. And so what I really need to do is this x coordinate minus 1. And so I'll say I'm going to do square root of y minus 1. That is, I just have my function minus 1. That's it. Notice again, I can't write x minus 1 here because if this is an integral with respect to y, everything has to be in terms of y. My formula, my differential, and my bounds. So to set up my bounds, I'm just going to have to think about, out of all the different circles that I could have had, that I could have drawn in here, and these are like radii of these different circles, how low and how high could they have gone? Well, if I look at this picture, I can definitely see that 9 seems to be the highest height that this region has. And down here, the lowest height that I reach seems to be whatever happens on my function, y equals x squared, when I plug in the number 1. So this would be at height 1. So it seems here that my bounds are going to go from 1 up to 9. This here would then represent a nice integral that is going to compute the volume of my 3D solid. This hopefully shouldn't feel any different than what we've done in the previous examples, and notice that I knew how to tell that this was a dy question by just thinking about the way that my disks here actually stacked up on top of each other. Now, I'm again not going to go ahead and evaluate this, but I'll leave that for you to go ahead and double check on your own. I ended up with a final answer of 40 pi over 3. Now, before we end this video, I want to go ahead and take a look at some results that we have on the next page. Because in all of these examples, we were illustrating something that we could refer to as the disk method. That is, we were trying to find volumes by adding up areas of circles given a little bit of thickness so they could become volumes. But a circle with a little bit of thickness is always going to have a shape somewhat like the following. It's going to have something that kind of almost looks like a cylindrical shape, but it's something that we would refer to as a disk. So this is what we call then the disk method. Now you don't necessarily have to read through all of this here. In fact, we've summarized most of this in the previous examples. But what you'll see is that if I had circles that stacked up horizontally, then it was going to be the case that I would have a dx question. And of course, since we were dealing with circles, I had area formula pi r squared. If I had a vertical axis of rotation, then I would have those disks stacking vertically on top of each other. And so then I would have a dy problem, but still I'm working with circles. So there really shouldn't be anything too new here. In fact, I would encourage you to not even really worry much about this particular box, but instead to focus on the idea of what's happening. The worst thing that students can often do in a section like this is try to start just hunting for random patterns. You instead want to try to say, I can see the 3D solid, I can understand the radius that's here, and I know that I'm trying to measure that. And when I can measure its length and figure out where those circles stack, I can easily set up the resulting integral. In the next video, we'll take a look at one small switch or complication that can happen when working with this disk method.